Today we're going to look at the parent functions from polynomials from Algebra 2, take a look at their domain and range, try to review them for you. Maybe you haven't seen a couple of them. The reason we're looking at all these parent functions is because one of the attributes of a powerful mathematician is the ability to find an appropriate model for a given situation. So we don't want to use a linear model for a situation in which a nonlinear model is more appropriate. So if we know the graphs of the basic functions, we can quickly connect visual information with equations to classify the functions appropriately. And we know that some equations only work for select values that are independent and dependent variables. Like you can't square a real number and get a negative answer. We also can't divide by 0, can't take the reciprocal of 0. And there are things in real life that limit the possible values of x and y, the domain and range. So here are 8 basic equations. I actually think there's 10, but I kind of am grouping. There's exponential growth and decay, so that's a exponential situation. And there's a linear function and a constant function, and both are really kind of from the linear family. So for each one, we're going to look at the key points and talk about their domain and range. So the first function that you should be familiar with is the linear function from Algebra 2. And sometimes in the textbook, it refers to it as the identity function only when it's y equals x. But linear functions also include anything that you could represent y equals mx plus b, right? Slope and y-intercept. So the identity function is the only time when you have y equals x. Any other time, it's just a linear function. Even y equals x, that's just a linear function. So if it's just the line y equals x, remember it has a slope of 1 and a y-intercept of 0. So I go through the origin and I go up 1 over 1 to make my points on my line. So that's the line y equals x. Its domain, so domain talks about the x-axis. So how much of the x-axis can be represented by this graph? And for this case, it would be all real numbers. So you can write all real numbers with the boldface capital R, which is represented with these 2 vertical lines here. You could also just write out all real numbers. You could write out negative infinity, comma, positive infinity with parentheses. All of those are ways to write all real numbers. The range represents the values on the y-axis that are represented by this function. This function keeps going up, 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 and down, 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 down. So it also has a range of all real numbers. So the second big focus of Algebra 2 should have been quadratic functions. So the parent function is y equals x squared. It's talked about in your book as the square function as well, because you're squaring the input. So I just wanted to make a quick sketch with the important points, thinking about if you plugged in points into x squared, what would you get? So its vertex is at 0, 0, because when you plug in 0, you get 0. And then hopefully you remember from Algebra 2, if you go over 1, 1 squared is 1. Negative 1 squared is also 1, because negative 1 times negative 1 is 1. And what about if I plug in 2? 2 squared is 4, so 2 comma 4 is a key point, as well as negative 2 comma 4. And another key point is 3 comma 9, because 3 squared is 9. So 3 comma 9 and negative 3 comma 9. So this graph has symmetry over the y-axis. It's called a parabola. It's a smooth curve. Its domain is all real numbers, because I can go out forever in either direction, and its range is starting at 0, it goes up forever. So y is greater than or equal to 0. Another way that you can write y is greater than or equal to 0 is with interval notation. A bracket 0 up to positive infinity with a parenthesis. So the bracket means that the function could hit 0, but the parenthesis means infinity is excluded. I can never get to infinity. The cubic function might be a little bit less familiar to you. So we're going to be thinking about if we plugged in points right around the origin, what would the output be? So if I plug in 0, I think you know that 0 cubed is 0, right? 0 times 0 times 0. If I plug in positive 1, I get 1. 1 cubed is 1. And if I plug in 2, 2 times 2 times 2 is 8. So 2 cubed is 8. If I go on the negative side and plug in negative 1 cubed is negative 1, because you have negative 1 times negative 1 times negative 1. So you get a negative result. And negative 2 cubed is negative 8. So this is a smooth curve through the origin. It reminds me of the tangent graph. Maybe you remember the tangent graph from trigonometry. The difference there is in trig, we use radians on the x-axis, and the tangent graph also has asymptotes for undefined values. The x cubed function does not have any asymptotes. So its domain can go out either way forever, and it goes up and down either way forever. So both the domain and range are all real numbers. I can plug anything I want into here. I could plug in positive numbers, I could plug in flat fractions, zero, negative numbers. I get an output for each. The square root function has a restriction on its domain. So could you plug in a negative number and take the square root of a negative number? No. So there are going to be no negative x values represented. The first number I could plug in is 0, and the square root of 0 is 0. And I'm just going to plug in perfect squares here so I get integer results, but you could plug in a half, right? The square root of a half, or the square root of 0.72. You could take the square root of decimals. So if I plug in 1, the square root of 1 is 1. Remember, a square root is a number times itself that gets you back to the original number. And the square root of 4 is 2, and the square root of 9 is 3. So those are the key points that I like to graph. This is actually a sideways parabola, or half of a sideways parabola. We can't really graph this part because then it wouldn't be a function. So the domain is all my x values have to be greater than or equal to 0. If you want to write that using interval notation, it would look like that. The range is that all the y values come out greater than or equal to 0. And if you wanted to write that in interval notation, you could. You only need to write it one way, so whichever way you prefer. So we're going to spend a lot of time looking at the reciprocal function. It's also called multiplicative inverse or inverse function. Rational functions when we come back kind of at the end of this and face-to-face. So here is what the parent function equation is. So for our purposes here, just recognizing that, hey, that's a rational function as opposed to absolute value or square root or something. So the inverse function, if I plug in 1 in the denominator, 1 divided by 1 is 1. And if I plug negative 1 into the denominator, 1 divided by negative 1 is negative 1. The rational function or multiplicative inverse function kind of looks like this, like two elbows in opposing quadrants. And when we talk more about them, we're going to see that they actually have asymptotes because there's a number in the numerator. So this fraction will never get to 0 because I would actually have to have 0 in the numerator to get to 0. And when you divide by a fraction, it's like flipping and multiplying by the reciprocal. So if you divided by like 1/10, that's actually going to be 10. So at 1/10, this graph should be all the way up here at 10. So you don't really, this is kind of a nice to know for now. We're not really going to be assessed on that until rational functions, but it is one of our parent functions this year. The domain and range are that x cannot be 0 and y can also, not be 0. And again, we'll come back to that again and revisit that function. Absolute value function, we're going to do more practice on a little bit later, but you should have seen absolute value function before. When you plug in a number, the absolute value tells you how far away from 0 you are on the number line. So the absolute value of 18 is 18. The absolute value of negative 30 is 30. So it's the positive distance that you are from 0. So the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. So there's a linear relationship going in this direction. What about negative numbers? So the absolute value of -1 is 1. The absolute value of -2 is 2. The absolute value of -3 is 3, and so on. So the absolute value function has a vertex at the origin, and it's a V-shaped graph with a slope of 1 and a slope of -1. So it can go out forever. So its domain is all real numbers, and its range, I never have any negative y values. So the y values start at 0 and they go up forever. So y is greater than or equal to 0 is my range. So exponential functions, we're going to study in a unit all their own. So for now, it's just, a couple of the parent functions or recognizing that something is exponential. In order to distinguish between exponential increasing, that's also called growth, or exponential decreasing, which is sometimes called decay, this is the base, and that's what tells you if you're going to have growth or decay. So if that number is 2 to the x, 3 to the x, 4 to the x, it's going to be a growth model. And if that number is a fraction between 0 and 1, like 1/2 to the x, you're going to get decay. So to graph these functions, I wanted to make a table of values just so you have the numbers written down. 0, 1, 2. -2, -1, 0, 1, 2. And the beauty of being virtual is you could always pause the video and take your time to graph these. So we have to actually define our base if we're going to actually graph it with a number. So for each of these graphs, I'm going to use a base of 2. So I'm going to call this y equals 2 to the x and this y equals 1/2 to the x. But this shape is going to be similar whether it was 3 to the x or 4 to the x. X is in the exponent. That's why it's called an exponential function. And so if I plug in a negative number into my exponent, the negative exponent rule says that you would first square the number. So 2 squared is 4. But the negative sign flips it over and makes it a reciprocal answer. So it actually would give me 1/4 because 2 squared is 4, and then the reciprocal is 1/4. -1, so 2 to the first is 2, and I flip it over 1/2. Anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. So when I graph these points, so 1/4, 1/2, 1, 2, 4, I get my curve that is exponentially increasing. And actually, you're never going to get to 0. So y equals 0 is something called an asymptote that we will study this year. So the curve is approaching y equals 0. So my domain is all real numbers. I could plug in any number I wanted. So the range is affected by this asymptote. My y values are all strictly above 0. So y is strictly greater than 0. If I wanted to write that using my interval notation, I need to make sure I put a parenthesis around 0 this time because I'm excluding 0 from one of the y values. So what happens over here when it's a decay function, it basically is these set of y values in reverse order. Because this time when I plug in a -2 as my exponent and I square it, I would get 1/4, but the negative flips it over and makes it a reciprocal. So same thing with the -1. Flip it over and it becomes the reciprocal, which is 2. Anything to the 0 power is 1. 1/2 to the first is 1/2, and 1/2 squared would be 1/4. So it basically takes this set of points and reflects it over the y-axis. So -2, 4, -1, 2, 0, 1, 1/2, and 1/4. And dotted line, y equals 0 is again my asymptote, and so it has the same domain and same range as the previous function. All right, so the last two of our parent graphs, the cube root function, and I forgot to write the function down, so the cube root of x. So if I think about the perfect cubes, it is basically the inverse of our x cubed graph. So think about it as this graph turned sideways. So if I take the cube root of 0, I get 0 again. I'm going to plug in perfect cube. So if I take the cube root of 1, I get 1. Well, what's the next perfect cube? The next perfect cube is 8. If I take the cube root of 8, I get 2. Same thing with negatives. The next perfect cube is negative 1. If I take the cube root of negative 1, I get negative 1. So I can take the cube root of negative numbers, but I can't take the square root of negative numbers. And the cube root of negative 8 is negative 2. All right, so there's my cube root function. See how it's reflected over the x-axis? Or sorry, it's reflected over the line y equals x from the cubic function. All right, and we will look at inverses again when we study exponents and logs. So I'll explain that a little bit more later this year. So the domain and range, again, are all real numbers for both. The last function I threw on here, so it's just called a constant function when y is equal to some number. So y equals 4, for example, it's just a constant horizontal line at 4. And the domain is always all real numbers. I can plug in any value that I want for x, but guess what? The range is always that y can only equal 4. So for a constant function, the y value stays a constant value. So why don't you take a look at the back page here, 1 through 4, and what you're going to do is identify what the name of the parent function is. So is it linear, quadratic, absolute value? And then state the new domain and range. So for example, I'll do number 1 with you, and then you can pause the video, try 2, 3, and 4 on your own, and then I'll just show you the answers at the end. So this parent function I think we know is absolute value. And what about its domain? Well, I should have drawn arrows here, but so it's going forever out. So domain is all real numbers. And it looks like the range goes down as far as 1, 2, 3, 4, negative 4. Y is greater than or equal to negative 4 would be the range. So take a minute, pause the video, and try 2, 3, and 4 before you check your answers. I'm going to pause the video and write in my answers right now. So you should be pausing the video. Pause it. All right, so here are my answers so that you can check a linear function, so all real numbers for both. This one is a quadratic function, all real numbers, y is less than or equal to 4, or negative infinity up to 4 with a bracket there. Square root function, it's been flipped, so x is less than or equal to 0. That's the correct interval notation. And y is greater than or equal to 1, and that is the correct notation for that one.